the Boolean ring problem number 55, which asks you to prove if any Boolean ring, which is entirely consistent, comprised of idempotent elements, is commutative. So we know that R is Boolean. That's or basically that if any A belongs to the ring, that A squared is equal to A. We need to show that R is commutative, or if we expand that out, we want something to that we can get our hands to work with. We have that x times y is y times x. So what can we use here? The puzzle pieces we're allowed to use if we start out with an arbitrary x and y and R is that x squared is x and y squared is y. Where we need to reach for is we have to show that x times y is y times x. I did spend quite a few hours scratching around like a chicken with no head and kept feeling that I needed commutativity to show commutativity. When we worked this out in class and I saw people working in groups, I saw kind of a similar experience. So that kind of seems to suggest that there's no genius. It's just kind of scratching around and everybody goes through the same thing. But it was kind of a nice observation, and I felt comforted by the fact that everybody was going through the same kind of scratching around. By scratching around, I mean exactly what we were doing in class, where groups were just playing around with their calculations and trying to get x times y equals y times x to happen. But I tried eventually to use what we used in the 328 lecture. Instead of working with x times y, I tried to do some kind of distributive law with x plus y. And so and I saw some of you do the same thing, that if you take x plus y squared and expand it out, you get x plus y times x plus y, and applying the distributive law, you'll get x times x plus y times x plus x times y plus y times y. There's a number of reasons you would want to do this calculation. You can do this, one, because you first got nowhere with working with just x times y, and two, that the note has stuff about squares, and three, we need something about x times y and y times x, and this does it all in one calculation that gets all of the things that you want to show and what you know into one equation. Well, here we are. I just repeated this calculation again. But by Booleanness, we know that x plus y squared is really x plus y. So summarizing what we really have that long expression in blue to the right is equal to x plus y. Well, x squared and y squared are the same thing as x and y, so I can drop out the x squared and y squared and replace it with x and y. And then I can subtract the x and y from both sides because R is an abelian group under plus, and cancellation by plus is okay. So that leaves me with yx plus xy, which gives me yx equals minus xy, which a lot of you actually got in class, and it was disappointing because really what you need is yx is equal to xy, not minus xy. So you felt a little bit sad there, almost, but no bananas. But I looked at this. I thought maybe this is something I can use. It's a property that I've derived. Maybe I can use it somewhere. Does this give me something? Well, if I use y equals x and set y equals x into this formula, I get that x squared is minus x squared, or x is minus x, because x squareds are the same thing as x. That gives me something very interesting. What that tells me is that every element, because x was arbitrary, is its own additive inverse. Now, I do want to point out that some of the people in the class, Rob Moore, had actually found this in a very different, slick way. So it doesn't mean that all scratching will be the same, but we got to the same place eventually. So if you do get a chance, ask Rob if you can take a look at his calculations, because they're much more slick than what I have here. Is it this easy? Oh yes, it's this easy. What is the additive inverse? xy? It's just xy. So minus xy is xy from the red boxed property. So we got it. Yx is xy. Done. So how do we write this up nicely? Of course, we don't show any sweat. It's supposed to be a piece of cake. Let xy be in R. We're going to show that xy is yx. Just remind the reader where we're heading. First, we're going to prove that xy is minus xy. We just leave them on a little bit. X plus y squared is expanded with the distributive law. And by the Boolean property, we have the following, which is x plus y with the Boolean property applied to x plus y squared. Just walking them along. And again, by cancellation properties in a group, we get xy is minus yx. And then we let the reader know we're going to set x equal to y, and we get x squared is minus x squared, which reduces by the Boolean property to x equals minus x. Applying the above fact to minus yx, namely that minus yx is yx, we have that the derived equation xy equals minus yx becomes xy equals yx, which was exactly what we wanted.